OCR Chemistry A 5.1.2 How far? Using Chemistry Explained means participating by writing notes and completing the tasks with a pen on paper or on a tablet. Pause and replay the slides at the pace that suits you. Most importantly, when prompted, pause the lesson, thinking a problem through, taking your time, completing the task before continuing and correcting your work. We'll start with a review of chemical equilibrium and the equilibrium law, look at mole fraction and partial pressure, a new equilibrium constant Kp, and homogeneous and heterogeneous equilibria. If we consider a general reaction equation in terms of A, B, C and D, we'll see here that we have reactant A, capital A and capital B, with their balancing numbers or coefficients, small a and small b, two products, capital C, capital D, balancing number small c, small d. So those are the four components at equilibrium, at constant temperature. The equilibrium law quite simply states that the concentrations of the right-hand side, that's the concentrations of C and D, raised to the power of their balancing numbers, divided by the concentrations of the left-hand side components, that's capital A, capital B, raised to the power of their balancing numbers or coefficients, equals a constant. Just to remind you, the square bracket is the symbol for concentration in terms of moles per decimeter cubed. That constant is called Kc, the equilibrium constant. So, for any starting concentrations of A, B, C and D, the same value of Kc is obtained at equilibrium. So you start with lots of A, lots of B, no C, no D. You'll end up with a Kc value at equilibrium that is the same as if you start with lots of C and lots of D and no A and B. However, temperature does affect the value of Kc. Hence, we have to specify earlier on that we are at constant temperature. So the value of Kc is maintained for any starting concentrations of ABCD at equilibrium at constant temperature. So let's look at an example. Consider the reaction between nitrogen, oxygen to make nitrogen 2 oxide. So a mixture of nitrogen and oxygen are allowed to reach equilibrium at a constant temperature. The equilibrium concentrations reached are, as written, 0.041 nitrogen, 0.0076 oxygen, 0.0047 moles per decimeter cubed nitrogen 2 oxide. Pause, calculate the value of the equilibrium constant. Restart when you're ready. Okay, so I'm going to reveal first of all the equilibrium constant expression. 2 nitrogen 2 oxide, so NO, concentration of NO squared, divided by concentration of nitrogen, concentration of oxygen. So there is our equilibrium constant expression. All I need to do is plug in the numbers. Make sure I do that without making an error. And then solve numerically. 0.0709. Now you may wonder what the units are. We'll come back to that on the next slide. So reviewing the units of equilibrium constant Kc from an earlier topic, but the methods employed will apply to Kp later on in this lesson. So if we look at the Kc expression here, we've got hydrogen iodide squared over hydrogen and iodine. If we look at the units, that's the units of concentration times the units of concentration divided by the units of concentration multiplied by the units of concentration. So we'll see that these cancel out. So we are left with no units. So Kc has no units in this case. So here's another Kc expression. Pause. Deduce the units for Kc. Restart when you're ready. Okay, so we've got Kc is equal to the concentration of two concentrations on top, three concentrations down below. So if I just do a little bit of cancelling, that leaves us with 1 over concentration, in other words 1 over moles per decimeter cubed. We can rewrite that as the units of Kc, bring it to the top line, so moles becomes moles to the -1, change the sign, decimeters becomes cubed, having changed the sign. So if we move from the bottom line to the top line, we change the sign of the power. So here's a problem. Calculate Kc given this reaction equation. A plus B goes to form C. So 1 to 1 to 1 mole ratio, reacting mole ratio. Initially there were 2 moles of A and 3 moles of B, and then at equilibrium there's 1.5 moles of B. From that data and the reaction equation, calculate Kc. Pause, restart when you are ready to see my worked example. Okay, so I'm going to set it out in this way. My initial numbers of moles of A is 2 moles, 3 for B and 0 for C. Now we're also told that at equilibrium there's 1.5 moles of B, which means that the moles of B have gone down by 1.5 moles, which must mean that C, because it's a 1-to-1 reacting ratio, has gone up by 1.5 moles. So if B goes down, C must go up. If B goes down by 1.5, it follows that A has gone down by 1.5 moles. So I know that B has gone down from 1.5 moles because we started with 3 and we've got, at equilibrium we've got 1.5. That's a decrease of 1.5. It follows that C has increased by 1.5 and A has decreased by 1.5 moles, which gives us 0.5 moles at equilibrium of A. That's 2 minus 1.5, and 1.5 moles of C at equilibrium, 0 plus 1.5. So I now need to turn those into concentrations. The volume of the container is 2 decimeters cubed, so divide by 2 to give us 0.25, 0.75 and 0.75 moles per decimeter cubed. So these are now concentrations. Form the Kc expression, put in the values, solve numerically, and for the units. Mole fraction and partial pressure. Mole fraction is the ratio of the moles of one component to the total number of moles in a gaseous mixture. So for component gas A in a mixture of gases, the mole fraction for A is the moles of A divided by the total numbers of moles of gas in the mixture. So let's do an example. Calculate the mole fraction of carbon dioxide and the mole fraction for oxygen in a mixture containing 2 moles of carbon dioxide and 8 moles of oxygen. It is straightforward. Pause, calculate the mole fraction for carbon dioxide and oxygen. Come back to check your work. Okay, so I'm going to reveal the mole fraction for carbon dioxide is the numbers of moles of carbon dioxide 2 in the total numbers of moles in the mixture, which is 2 plus 8. So 2 divided by 10, the mole fraction of carbon dioxide is 0.2. Now there's another way that we can calculate the mole fraction for oxygen, because mole fractions in a mixture must sum to 1. So the mole fraction of oxygen is 1 minus the mole fraction of carbon dioxide. It's a 2-component mixture, comes to 0.8. So the mole fraction of oxygen in the mixture is 0.8. The pressure exerted by gas A in a mixture of gases is called its partial pressure. So we indicate that as P subscript A. So that's the partial pressure for gas A, the pressure exerted by gas A in a mixture of gases. The total pressure of a mixture of gases, ideal gases, that is gases that do not interact significantly, or ideal gases do not interact with each other. So we've got 3 gases I'm proposing, A, B and C. So the total pressure is simply the sum of the partial pressure of A plus the partial pressure for gas B and the partial pressure for gas C. We know from the ideal gas equation, PV equals nRT, that the numbers of moles of a gas is proportional to the pressure exerted by the gas. So if we know the mole fraction, the moles of A as a fraction of the total moles, because the numbers of moles is proportional to the pressure exerted, we know that the partial pressure of A divided by the total pressure of the gas system will give you the same value. So the mole fraction is also equal to the partial pressure of gas A. The mole fraction for gas A is equal to the partial pressure of gas A divided by the total pressure. We can rearrange this, and this is the form that it's most useful in. The partial pressure, the pressure exerted by gas A in a mixture of gases, is its mole fraction times the total pressure. That expression needs to be known and is most useful. So let's start with a simple problem. If for dry air the mole fraction for nitrogen is 0.78, calculate the partial pressure of nitrogen gas at an atmospheric pressure of 740 millimeters of mercury. Pause, calculate the partial pressure for nitrogen. So I'm going to reveal the partial pressure of nitrogen is simply the mole fraction times the total pressure. Mole fraction times total pressure comes out as 577 millimeters of mercury as the partial pressure of nitrogen gas in the atmosphere. So let's look at a second problem. We've got a mixture of methane and oxygen. This time we know the partial pressure of methane at 0.175 atmospheres and the partial pressure for oxygen, 0.25 atmospheres. Calculate the mole fraction for each gas in the mixture. Crucial to that is the use of the expression the partial pressure of methane or of any gas is the mole fraction for that gas times the total pressure. Pause, calculate the mole fraction for each gas, come back to check against my working. So I'm going to reveal the total pressure. We need to calculate the total pressure. If we're going to use this expression, we need the total pressure. The total pressure is the sum of the partial pressures. So the total pressure is the partial pressure of methane plus the partial pressure of oxygen, comes to 0.425 atmospheres. The mole fraction of methane is the partial pressure of methane divided by the total pressure. So I've just rearranged this expression to give me the mole fraction as the partial pressure methane over the total pressure. So that's 0.175 over 0.425 comes out at 0.412. Similarly, for oxygen, 0.25 divided by 0.425 gives us our partial pressure for oxygen. You'll see that those two partial pressures sum to the value 1. So we'll move on to look at the equilibrium constant in terms of partial pressures, that is Kp. The equilibrium constant can be expressed in terms of pressure units, in which case it is denoted Kp. So if we look at the decomposition of dinitrogen tetroxide into nitrogen dioxide, and we write an equilibrium constant expression, instead of Kc, we've got Kp, so the units are not concentration, but partial pressures. So we've got nitrogen dioxide squared, the partial pressure of nitrogen dioxide squared, divided by the partial pressure of dinitrogen tetroxide. The units in the case above, we would work out in exactly the same way as for Kc. And this is true for any units of pressure, and you'll see a variety are used even in the exams, but let's stick with atmospheres. So we'll have a partial pressure for nitrogen dioxide in atmospheres squared divided by the unit of partial pressure for dinitrogen tetroxide in atmospheres. So atmospheres squared divided by atmospheres gives us a unit of K for Kp as atmospheres. Now, as with Kc, Kp is a constant value for any starting quantities at a particular temperature, because changes in temperature and only changes in temperature will affect the value of Kc and therefore also of Kp. So here's a problem which I'd like you to try and solve. Calculate the value and the units of Kp for the contact process given the equation and the partial pressures at equilibrium. So I need to give you those. So here is the equation for an industrial process called the contact process. 2 sulfur dioxides plus oxygen gives us 2 sulfur trioxides. At a particular temperature, the equilibrium partial pressures 0.273, 0.402 and 0.325. Pause, calculate the value and work out the units for Kp at this temperature. So I'm going to reveal. I need to write a Kp expression. So I've got 2 moles of SO3, so partial pressure of SO3 raised to the power of 2 On the left-hand side, I've got 2 SO2 and O2. So all expressed in terms of partial pressures. Put the values in, 0.325 squared divided by 0.273 squared and 0.42 times 0.42. Numerically, that comes out as 3.525. What are the units? Hopefully you've done that. If not, pause. I'm going to reveal the units. Atmospheres squared divided by atmospheres cubed. So 1 over atmospheres, atmospheres to the minus 1. So here's a second problem. An equilibrium mixture in the contact process was found to contain 2 moles of sulfur dioxide, 2 moles of oxygen, and 5 moles of sulfur trioxide. The pressure 200 atmospheres and the temperature 1000 Kelvin. Calculate the value of Kp for the contact process at this particular temperature. Give you a quick clue at this stage. Work out the mole fractions at equilibrium and then calculate the partial pressures at equilibrium, and from that achieve Kp. So there's your plan. Pause, carry out the calculation, come back to check against my worked example. So you should have worked out that the mole fractions for sulfur trioxide, the total moles is 9. That's 2 plus 2 plus 5. So the mole fraction for sulfur trioxide is 5 divided by 9. For sulfur dioxide, 2 divided by 9. And similarly for oxygen, 2 divided by 9. If we know the mole fractions and the total pressure, we multiply those together to give us the partial pressure for sulfur trioxide at equilibrium, for sulfur dioxide, and for oxygen. There's the contact process equation from the previous slide. Hopefully you recalled that. There's the Kp expression. Put these partial pressures in, comes out as 0.141 atmospheres to the minus 1. So here's a third problem. We're going to look at the Haber process, nitrogen and hydrogen forming ammonia. Initially 21 moles of nitrogen, 63 moles of hydrogen reached equilibrium and were found to contain 24 moles of ammonia at equilibrium, all at a constant pressure, that is a total pressure of 180 atmospheres. Calculate the value of Kp at this temperature. Pause, think it through, come back to look at my modelling. Okay, so I'm going to reveal the first part of the calculation, which is to set it out in a way that can then be interpreted clearly. Initial moles, 21 of nitrogen, 63 of hydrogen. I'm double checking as I speak, and 0 of ammonia. At equilibrium, we are told there's 24 moles of ammonia. So we've increased by 24 for ammonia. That means the amount of hydrogen must have gone down by 36. It's a 2:3 ratio. So if ammonia increases by 24, hydrogen must decrease by 36, and it also means that the nitrogen must decrease by 12. It's a 2 moles of ammonia are formed from 1 mole of nitrogen. So 24 moles of ammonia are formed. We must have lost 12 moles of nitrogen, which leaves us with, at equilibrium, 9 moles of nitrogen, 27 of hydrogen, and 24 of ammonia. Now, if you haven't successfully calculated Kp yet, now you've got that information, pause, complete the calculation. Otherwise, I'm going to reveal So my mole fraction of ammonia, 24/60, total moles is 60. Hydrogen, 27/60, and nitrogen, 9/60. That gives us these moles fractions, from which I derive the partial pressures, mole fraction times the total pressure, giving us these partial pressures at equilibrium. Form the Kp expression. Check that you've got that correct. Put in the partial pressure values, solve numerically, and the units, of course, are atmospheres to the -2. I might advise doing some practice questions at this point. If you have access to the OCR Chemistry A endorsed textbook, then you'll find summary questions 1, 2 and 3 on page 301. The answers are provided on page 757. Of course, other textbooks will also have suitable questions. Homogeneous and heterogeneous equilibria. Homogeneous and heterogeneous equilibria, such as the one seen in the Haber process, nitrogen and hydrogen forming ammonia, are termed homogeneous in that all the components, nitrogen, hydrogen, ammonia, are all gases. They are in the same phase. However, equilibrium may contain a mixture of phases, may contain solids or liquids, and these are termed heterogeneous. So we've got the decomposition of calcium carbonate forming solid calcium oxide, but gaseous carbon dioxide. As solids and liquids have fixed concentrations at any particular temperature, they are omitted from the heterogeneous equilibrium expressions. So the equilibrium constant expression for the decomposition of calcium carbonate is simply Kp equaling the partial pressure of carbon dioxide. Calcium oxide being a solid is omitted. Calcium carbonate being a solid is omitted. So let's look at a calculation involving heterogeneous equilibria. So a quantity of carbon was heated at 1000 Kelvin, reacted with steam. So here's the equation, steam and carbon giving us hydrogen and carbon monoxide. The equilibrium partial pressures of steam, hydrogen and carbon monoxide were found to be 14, 8.2 and 6.4 atmospheres respectively. Calculate Kp. Pause, carry out the calculation, then come back to check against my modelling. Okay, so I'm about to reveal. I'm writing my Kp expression. Partial pressures for the right hand side divided by partial pressures for the left hand side, but I'm omitting carbon. It is a solid. So carbon is a solid, I am omitting it. And then plug in the numbers for the partial pressures, calculate 3.75 atmospheres. The effect of conditions on Kp. So if we look at the Haber process, which is nitrogen and hydrogen forming ammonia, we know Le Chatelier's prediction for the effect of a pressure increase would be that the equilibrium will move to the right, forming less moles of gas and therefore countering the pressure increase. So there's the qualitative prediction from Le Chatelier. We can explain this by considering the Kp value. So here's the Kp expression for the Haber process. It would appear that if we doubled the total pressure, the value of Kp would be decreased, because we're going to be doubling the partial pressure of ammonia, which is squared, but also doubling the partial pressure of hydrogen, which is cubed, and multiplying it by a doubled partial pressure for nitrogen. That would appear to indicate that Kp would be reduced. However, the equilibrium moves to the right, increasing the partial pressure of ammonia and decreasing the partial pressures of hydrogen and nitrogen. So the equilibrium moving to the right increases the value for the partial pressure for ammonia, decreases the partial pressure for hydrogen, and decreases the partial pressure for nitrogen, thereby adjusting the partial pressures so that the value of Kp is maintained. So I'll just run through that again. It would appear that doubling the total pressure would change the value of Kp because you're doubling each of the partial pressures, and because we've got different powers raising those partial pressures, the value of Kp would alter. However, the equilibrium adjusts or moves to maintain the value of Kp. It can do that by shifting from left to right, increasing the partial pressure of ammonia, decreasing for hydrogen and nitrogen, so thereby maintaining the value of Kp. And that explains the qualitative effects of Le Chatelier's prediction. On the other hand, changes in temperature are known to alter equilibrium constant values, Kp values. So if we look at the Haber process, and we've got delta H indicating that the forward reaction is exothermic, then by Le Chatelier, increasing the temperature at equilibrium would move the equilibrium in the endothermic direction to the left. So the partial pressures of hydrogen and nitrogen both increase while the partial pressure of ammonia decreases. And as Kp is the partial pressures of ammonia divided by those of hydrogen and nitrogen raised to their coefficient powers, the value of Kp is decreased. So for an exothermic reaction, increasing temperature at equilibrium decreases the value of Kp. A vice versa argument, obviously, for a decrease in equilibrium temperature, Kp would be increased. So here are some predictions for you to make. Predict movements in the position of equilibrium and the effects on the Kp value for the dinitrogen tetroxide nitrogen dioxide equilibrium, which we are told is endothermic in the forward direction. What will be the effect of increasing pressure on the position of equilibrium and the value of Kp? Similarly, for an increase in temperature and the addition of a catalyst. Pause, make your predictions, come back to check against my answers. So I'm about to reveal. If we increase pressure, the position of equilibrium will move to the left to maintain the value of Kp. There's no change in the value of Kp. If we increase temperature, the position of equilibrium will move in the endothermic direction. It will move to the right, and that, of course, will increase the value of Kp. The addition of a catalyst has no effect on the position of equilibrium and therefore no effect on the value of Kp. The effect of adding a catalyst is to attain the position of equilibrium at that temperature, but more quickly, faster. You will find some suitable practice questions under the heading Summary Questions in the OCR Chemistry A endorsed textbook, questions 1, 2, 3 and 4, page 306. You'll find answers on page 575. If you don't have access to the OCR A endorsed chemistry textbook, then other textbooks will also have suitable questions. If necessary, go through this lesson once again. That's your decision. Complete some practice questions from any suitable textbook before moving on to the next topic. That next topic is your choice. Any feedback you'd like to give me, I'm available at that email address. Thank you very much.